this last session of the day. We have 3 very interesting talks. And the first speaker of the session is Olivaine de Queiroz from Campinas. He will be talking about hard type inequalities versus approximation procedure in the study of class of free boundary problems. Okay, thank you, Olivaine.
So, thank you, Ricardo. So first, let me thank the organizers for the opportunity they gave me to be here to present my work. For those who was in Argentina at the beginning of the year, there will be some intersection, but I hope it's not so big, so I hope you enjoy the talk. Today I'm going to talk about some regularity results for a class of free boundary problem. I am interested in both elliptic and parabolic problems, okay? I have several motivations for this kind of problem, but let me connect my talk with the one by Damião. During his talk, he told something about the equation, some equation like this, Laplacian of u equals to gamma, u to the gamma minus 1, with, for instance, gamma between 0 and 1. And he told that the solutions for these problems are C1 alpha, with alpha equals to gamma over 2 minus gamma. Okay? And as Professor Caffarelli told it, when gamma goes to 1, you have the obstacle problem, and you have C11 regularity. When gamma goes to 0, you have a kind of cavity problem here, and the solution is just C01. Okay? For the problem that I'm going to consider a kind of limit of this kind of problem, but not in the sense that I'm going to send gamma goes to 1, but I'm going to consider a singularity here, which is not like a power. It's something like log of u plus, okay? And, okay, this is the mathematical motivation for this kind of problem, but I have several motivations, okay? And I'm going to talk a little bit more in a few slides, okay? So in the general context, I have this kind of problem. I'm going to consider the parabolic and the elliptic problem. And when I have the reaction term here, which goes to minus infinity when z goes to 0 plus, okay? And the example is f of x of u equals to log of u plus, okay? Just one phase for today. Okay, as I told, I want to study optimal regularity for solutions of both problems, okay? And so just to recall here, Laplacian of u equals to log of u plus, or something like, I need to put here some minus, yeah. Probably something like this. Okay, I would like to study optional regularity for solutions of this kind of problem. And if you see here, solutions are not expected to be C11 like the obstacle problem, because you have the singularity here when u goes to 0, so the Laplacian of u, at least for the elliptic problem, blows up, and then you don't have that the second derivatives of u are bounded, and you cannot obtain C11 regularity, okay? But if you see this kind of problem here, you see that when gamma goes to 1, you kind of obtain C11 regularity. And if you compare the two nonlinearities here, you see that log of u is not so strong as u to the power gamma minus 1 when gamma is close to 1, okay? So it's expected that solutions for this kind of problem has a better regularity than the one for this kind of problem. But since I have, this is not so strong as this kind of power for each gamma, then is it expected that the solutions for this kind of problem is still 1 alpha for each alpha between 0 and 1, okay? Because this ranges from 0 to 1 when gamma varies between 0 and 1. Another motivation, if you like, for instance, to study for further equation, you have this kind of problems in thin films, in dynamic of thin films. And this problem here can be considered as a kind of limit for this kind of problem. For instance, if you suppose that f is some power and g is some power, and you have this kind of relation between the exponents here, if you consider just steady states for this kind of equation, then you are going to see that solutions for steady states for this problem needs to satisfy this equation. And then if you take nu and mu with this relation, you are going to obtain that H satisfies this kind of equation. Okay, see, you can see this in this paper by Berthoz and Pugy. Well, this is just for this is the motivation for the elliptic problem, okay? But in some chemistry reactions, you can see that it appears some kind of some problems like minus Laplacian of u equals to some f of epsilon u, and this f behaves like something like this kind of graph. And when epsilon goes to 0, you see that this behaves, it blows up when epsilon goes to 0. This kind of problem appears in chemistry reactions, and this, you can find this in this book by Juan Diaz. Okay? This is another motivation so for this problem. Okay, but I have an important general remark that is the following. When we consider free boundary problems, for instance, this class of free boundary problems, the scale of the equation is very important in the study of the free boundary. Okay? For instance, if you have the obstacle problem, you have that the scale of the equation is something like r to the power 2. If you have cavity, you have just r. And if you have this, with this gamma here between 0 and 1, you have that the scale of this equation is like this alpha. But in our case, this problem does not have a scaling property, so we cannot use the same methods that we can use here to study those problems. But this is not the first problem where you can find this non-characteristic growth of the solution. There is an example in this paper by Monod and Weiss, where they studied this, they called unstable free boundary problem, which is the obstacle problem with the minus sign here. And they show that there are some points, some free boundary points, where the solution grows like r squared to the power r squared times log of r away from the free boundary. They call this super characteristic growth. Okay, so there are some examples where in some free boundary problems that close to some free boundary point, the solution behaves like this. But in this paper here, you see that there are just some free boundary points where this kind of behavior holds. And we mentioned that what we are going to show is that solutions for this kind of problem has super characteristic growth at every free boundary point. So you have an interesting prototype that where you can find super characteristic growth at every free boundary point, and then we would like to develop some techniques to study this kind of problems. Okay. So let me start with the elliptic case. And for the elliptic case, let me tell you that unfortunately, I cannot prove regularity. I'm going to treat just regularity of the solution, okay? And we was not able to prove regularity for any solution of this kind of problem, even for the elliptic case. We started just with minimizers for this functional with the Euler-Lagrange equation for this functional is this one here. And we proved regularity for minimizers, okay, in the elliptic case. Okay, so we have this functional here that we want to minimize in this class of functions with some boundary data. And I'm going to present our main results. By the way, I forgot to say, this is a ongoing project with Henrik Chagolian. The elliptic case is ongoing work with Henrik Chagolian. And the parabolic case that I'm going to tell also is ongoing project with César Soares, a student in Campinas, and Ângelo Roncalli de Holanda from Federal University in Campina Grande. But I'm going to present, to give the credit exactly when I show you the theorem, okay? So this is the first theorem that we was able to prove. We showed that minimizers for the functional that give rise to this Euler-Lagrange is C1 log Lipschitz. This is a modulus of continuity that Tatiana Toro told today, and also I think José Miguel Urbano also told yesterday. We was able to prove this kind of regularity. And okay, we have regularity for minimizers and also non-degeneracy estimates for minimizers, okay? And let me point out that this is the optimal regularity for this kind of equation because I have this example here, okay? Since we have, it was expected that the solution was C1 alpha for each alpha between 0 and 1. This is not optimal, of course. And what we showed is that we have C1 log Lipschitz regularity, which is the best possible because we don't have C11, okay? Even in this, without using scaling properties of the equation, okay? So the first part of the title was Harnack type inequality, and that's because we proved this theorem with using a Harnack type inequality, okay? And let me just tell you how we proved it. I'm not going to show the proof, but I'm going to show the steps of the proof. Okay, let me emphasize also that we don't have polynomial growth in every free boundary point. We have just this kind of super characteristic growth. And okay, I have the lack of scaling of the equation. But another point that is interesting is to mention that when you consider this problem here, the Euler-Lagrange equation, we have that the right-hand side changes sign when u is bigger than 1, for instance, okay? So this is another complication to prove the estimates. Okay, the first step is this lemma, which gives rise to the Harnack type inequality. And the lemma says the following. Take a minimizer u and let us consider the mean value of u on the boundary of any ball, and suppose that this is greater than this constant here, which is related with is not constant, actually is a function of the radius. If you have that the mean value of u on the boundary of the ball is greater than this modulus of this function of r, then you are going to have that u is strictly positive, and you know how to control the function, the minimizer u from below with this constant here, okay? This holds for almost every point on the ball. This is something like, okay, I don't have Harnack type inequality because solutions here can, the right-hand side can change the signs, but we have that if the solution, if the minimizer is somehow big on the boundary, then you have Harnack type inequality. Okay, I'm not going, this is not Harnack type inequality. Harnack type inequality is in the next slide, but this is, this lemma here will imply Harnack type inequality, which is this one. Okay, so suppose that U is a minimizer, and suppose that U is not so big. Okay, this is possible because, first of all, you need to show that U is continuous. So this is possible close to a free boundary point. Then you have that. Then you have this Harnack type inequality, and in particular, if you assume that you are centered in a free boundary point, then you are going to have that U has this growth away from the free boundary, which is almost the log Lipschitz regularity that we wanted, okay? Okay, let me just tell you how to prove this kind of Harnack type inequality. But first of all, let me say that this is also goes back to a work by Alt and Phillips. And recently also Ray Young proved this kind of result in his thesis, working with the fractional Laplacian. In our case, the things are a little bit different because we don't have scaling, and scaling for in the proof of Alt and Phillips and Ray Young, the scale of the equation is very important. It plays a very important role, but we don't have scaling here, so we need to prove to construct a subsolution using another kind of argument, okay? And the way we do this is the following. First we try to use a scale, okay? Then we take this function here, which we thought that it was the nice scale for the equation, and we plug this into the functional. And we see that if U is a minimizer for J, then UR is not a minimizer for a change of variables of J, but for another kind of functional, which is this one here. Okay? So you don't have that a scaling is a minimizer for a similar functional, but to another one, which is this one here. Okay? So we started to study this kind of this functional, and we showed that, okay, this is a technical lemma which says that if you have some growth conditions for any function U which is in 8.1 of the ball, if you have this kind of growth, then you can construct a local subsolution for this kind of problem here, which is not the one that we wanted. We wanted this problem with theta equals to 0. We don't have it. Okay, but we have this for each theta. For every theta that you take, I can find a subsolution for this problem if we take r small. Okay, this is the distance function. Okay, so this is a technical lemma. Once we have this, we would like to if theta was 0, then what I'm saying is that the W is a subsolution for this problem, and then we could proceed with the argument like Alt and Phillips and Ray Young, but we don't have this. Okay, what we have is that W is a subsolution for the Euler-Lagrange equation of this functional here. Okay, this is exactly what this lemma says. Okay, so take the functional, take this theta, take one theta, and then you take that theta here and find W, and then W will be a subsolution of the Euler-Lagrange equation given by this functional here. Okay? Once you have this, you just take theta equals to minus log of r squared, come back here, and see that this is exactly what you want, okay, when you take the scaling. So you have a local subsolution for your problem. If you have a local subsolution for your problem that has this kind of growth, then you can prove the Harnack type inequality. And once you have Harnack type inequality, you get regularity, log Lipschitz regularity for the solution, okay? This is just the idea of the proof of the log Lipschitz regularity. Okay, so now we want to study the parabolic case. And the problem is that I don't know how to prove Harnack type inequality for this kind of Harnack type inequality for parabolic problem, for the parabolic problem. And then what we did is the following. So this is the equation. I want to study ut minus Laplacian of u equals to log of u plus. And I don't know how to prove Harnack type inequality for this equation. And this is somehow related with the this kind of equation here has some kind of non-degeneracy like the one in porous medium equation or the one in ut minus p Laplacian of u equals to 0, okay? And somehow this is related with the intrinsic Harnack type inequality that José Miguel Urbano told yesterday. So this is, I think that this is because that's why to prove regularity using Harnack type inequality is a kind of tricky. So we decided to do in another way. We constructed an approximated problem. And this approximation here needs to be exactly this one. Otherwise, we don't have a local subsolution for the problem. And then we don't know how to prove existence of a solution. Okay, but when you have this kind of beta epsilon here, you plug in the equation, then our argument is the following. We prove this problem has a solution using classical theory. Then we can prove uniform estimates in epsilon. And then we can send epsilon goes to 0 and find a candidate for the solution, okay? The idea is prove regularity estimates independent of epsilon to solutions for this problem here, and then try to prove that in the limit you have that this kind of regularity is conserved, okay? Some estimates that we need, this one is not so difficult, just to use Poincaré inequalities and Gallardo-Nirenberg type inequality. Once you have this kind of estimate, you can prove using Moser interaction L infinite bounded for the solution, independent of epsilon. And once you have this, you have that the solution, you can find a solution, and the solution is at least C3 for the class, using the classical theory. And then you can prove this gradient estimate, which is proved using a kind of Bernstein type technique. It's by contradiction, actually. And see that, okay, there is a constant here, which depends on the initial data. And you see that this function here is strictly positive, is a test function, but it is strictly positive on the domain. So you can, if you take an omega prime that is compactly inside omega, then this psi here is strictly positive. You can bound it from below, and you see that gradient of u epsilon squared is less than some constant times minus u times log plus some constant u. Okay, that's the point. This is the gradient estimate. Okay, this gradient estimate is useful not just for the regularity, but also to pass to the limit in epsilon when you want to show that the limit is a solution. Okay, you see that you need a control on the gradient to show the existence of a solution in the limit. Once you have, you need to prove this first, okay? And once you have this kind of gradient estimate, you can prove an estimate in time, which is this one. Okay, it's very natural. It's not so easy, but it's natural to prove. It's natural. The point is that this kind of estimate here is not so easy. We need to prove this. In the case of the power type nonlinearity, we need to use a kind of scaling, and here we don't have scaling. So what we did, we tried to adapt this Harnack type, this intrinsic scaling by Di Benedetto, and we proved that UT satisfies this kind of estimate here. Okay, this is what I said. And once we have this, we can prove that the gradient of U has this kind of growth close to a free boundary point. And okay, let me tell you also that this estimating time here is also, with this kind of estimate, we was also able to prove that U epsilon is C0 alpha uniformly in epsilon. I mean, the C0 alpha norm of U epsilon is independent of epsilon, so you can pass to the limit once you have a limit solution, and the limit will have the same type of regularity. And once we prove this, we can prove that the gradient of U grows away from the free boundary like this modulus like this rate, okay? And with this, we was able to prove that the solution, the limit solution is C1 log lib in X and C0 alpha in T for any alpha between 0 and 1, okay? Let me just do some words quickly here. Okay, we was not able to prove the optimal regularity in time, okay? Let me just give you a summary what we have done. Okay, this is just to remember. Next time that you saw me, you recall this last slide, I think. Okay, we consider elliptic and parabolic free boundary problems with logarithmic type nonlinearity, and I think that this is important because it's a prototype of problems that exhibit non-polynomial growth close to the free boundary. Okay. In the case of the elliptic problem, we proved the regularity, the optimal regularity using Harnack type inequality, and and we constructed for this a kind of local almost subsolution. We was not able to prove the regularity of the parabolic problem using the Harnack type inequality, and since we did not use Harnack type inequality, we was able to prove just regularity for a limited solution. Okay, and the limit to prove the regularity, we have used a kind of intrinsic scaling. The parabolic problem. For the parabolic problem, we approximated it, and then we proved uniform in epsilon estimates, passed to the limit, and then we have obtained that a solution for the parabolic problem is C1 log Lipschitz in X and C0 alpha for every alpha between 0 and 1. Okay, so I think it's just this. Thank you.
Thank you. So, any questions for the speaker?